We'll get started. Welcome, everyone. Welcome to our outstanding community developers, our enterprise customers, and those who have been with Particle for quite a while. Today, we're going to walk through how to design an IoT product around the Particle B series in 45 minutes. This will be led by myself as one of the solutions architects. I'm Ethan, and Mohit, one of our professional service and early founding engineers with Particle. Will be walking you through how to build a product pretty rapidly based on the Particle B series. So when we take a look at the Particle product portfolio, we have two form factors that primarily customers scale on. The first is the Feather form factor, which is great for prototyping. It includes power management IC and a battery connector. In addition, there's an onboard BLE antenna. We also include the LEDs and mode and reset buttons. But what we found is on the we have an M.2 form factor that allows you to have quite a bit more flexibility. That module for the M.2 form factor is ready for mass production. You are able to have ownership over your power system. So in terms of which battery you use, what power electronics you use in order to power it, in addition to ownership over connector and button placement. And lastly, we have the ability to you have the ability to swap out modules based on the deployment region with the M.2 form factor. But I have a question for everybody. Hopefully, we'll have quite a positive responses. Have you used a particle boron before? Hopefully, be really excited to see. If we've launched a poll. All right. It's always really exciting to see who's built on Particle and who's never used Particle before. We're really excited that everybody's here, and it's also really fun to hit those buttons. Wow, so it looks like we've got a nice split. We'll share those results so you can have an idea of what your fellow webinar mates, what their perspectives are. So this is great. So we've got quite a number of new individuals building on top of Particle. So we'll dive in a little bit more into, now that we kind of have a framework, as we'll dive in a little bit more to the M.2 advantage and kind of why we picked for this product or this webinar, building on top of the M.2 SOM. The value really is that it's a super compact module with a super high density connector design. The value is that it's designed to be modular, so that you can, again, swap out those modules, and as new technologies come out, purchase those modules, and really have the flexibility to use the key components that we want in terms of adding buttons, where the LEDs need to go. So we have a lot of fine-tuned control over placement. And lastly, you'll want to think about kind of where you're going to deploy your product. So when you are building your IoT product within the Particle B series ecosystem, the primary driver is deployment region. The first module that we introduced in this form factor is the B402 B series, which is built on top of Cat-M1. And that's primarily driven for North America, where Cat-M1 has been the most mature. And then we have a second SKU, which is in that same form factor, which is intended for Europe and regions where 2G is still available outside of North America. The value on this is really, you're running the same Particle device OS and your own custom application firmware on the Particle device, and you're able to swap them out seamlessly and put the firmware onto B523 for a European customer, and put your same application firmware onto a B402 for a North American customer. Next slide for me. Perfect. So Mohit and I are going to walk you through exactly what this product is that we built, and we're going to go through the entire lifecycle process that Mohit used in order to build a product. That includes going over the system architecture, going through the product architecture, walking through his key component selection for the device, walking through his schematic design in terms of how components are placed and connected, going through the board layout, and finally walking through the mechanical product integration to actually put all these pieces together to bring it to pull it all together and make a finished product. And with that, Mohit, please take it away and help everybody learn how to build something quick. The timer starts now.
All right, 45 minutes. Thank you, Ethan, for the great introduction. I'm super excited for this particular webinar because, we are going to learn how to design the hardware around the B series. And, hardware is near and dear to me. I've been with Particle for about 7 years. Most of my time was spent on engineering. And now I spend my time on studios where we build products, turnkey products for our customers. So let's see what this B series is all about. Most of you have used a um, particle boron before. Um, and it seems that particle boron is in a feather form factor, quick to prototype. But what if you needed more flexibility in terms of power management? You needed more GPIOs. You needed different antennas. So the B series is a condensed version of the boron. We have two flavors. One is the U-Blocks, using the U-Blocks R410, and then the second one is using a cocktail module. Depending upon where you're deploying the B series, you'll select one or the other. We'll walk you through like how the selection process will go, but this particular module just needs power and antenna to function. So as long as you are able to provide the VCC 3v3, this module is good to go. But before we start building around it, like let's take an example case that we can use to deploy a product. For example, say you have a old legacy device out in the field and you want to bring it online. How would one achieve this with Particle B series? Say, for example, this legacy device is a compliance monitoring equipment, at a gas station, or it's at an oil refinery, or it's just gathering data from an old equipment that talks a legacy language. This legacy language could be, the age-old RS-232 protocol, and RS-422, RS-485, or even CAN. So today we will see what does it take to talk to a legacy device through this legacy protocol, and how can we build a complete product from ground up around it. A architecture of such a product would look like, you obviously need the Particle B series. You need a couple of power regulators, one to power the modem, and then the second to power the peripherals and the MCU. Then obviously we'll need an antenna, some form of a driver receiver, depending upon what legacy protocol you're using, and a few user interface components like LEDs and buttons. But first, how do you select which Particle B series SOM to use? It's quite an easy decision. We already know that we are going to use cellular, and so that decision has been made for us. If you wanted to use Wi-Fi or Ethernet, that would be a different conversation. And based on the region, right now we are in North America, so it's an easy pick. We'll be using a B402. But if you were outside of North America and you had access to, say, Cat1 network, or if you had legacy networks like 2G and 3G availability, then you will be using the Particle B523 to be deployed. But the base design for both of these would be the same. So all you'll need to do is swap out the module. So we'll use the LTE Cat M1 B402 module that's based on the U-Blocks Seraph R410, and we'll be deploying this in the North American region. Next comes the 4-volt regulator. This particular regulator will only be powering the modem, in this case, the Seraph R410. You need to make sure that all of these design choices as we make are relevant to the modem that you're using. And so how do we choose that? It's a quite an straightforward decision. Say if you have a primary source, is this device going to be plugged in into the wall at all times? If no, then you'll be using some sort of a backup battery. If yes, then is the source greater than 5 volts? If it's greater than 5 volts, I think then um, we would recommend using a switching or switch mode power supply. If it's less than or equal to 5 volts, then we'll go for a linear low dropout regulator. What are the differences in these choices, or what are the things that we need to remember? All of today's cellular modems are tuned to be working on a single cell lithium polymer battery. Usually it operates at 3.7 volts. This is just because all of our devices today are portable and they are being powered by lithium polymer batteries. And so that makes the most logical sense for the vendors. If you are choosing a battery, you need to pay attention. You can't just use any battery. If you're using a lithium polymer, you need to make sure that it can meet the peak current requirements. For example, the B523 has peak current requirements of 2 amperes when operating in fallback 2G mode. For R410, those requirements are a little less. And then many times the batteries have internal protection circuits. So if you have a MOSFET on its output, and if it's causing a voltage drop of more than 400 millivolts, you need to make sure that doesn't happen. If the input voltage is at 5 volts or lower, then you can use a linear LDO. Again, make sure that it meets the current requirements, and the power dissipation that occurs should also be considered. If you're using a switching, there are slightly few more criteria that need to be passed. In addition to current, you need to make sure that switching frequency is above 600 kilohertz. This is to make sure that the modulation that happens on 2G and 3G bands are not affected. You need to make sure there's a low ripple on its output, and preferably using a PWM mode. So for us today, we to keep things simple, we'll just go with an LDO, because we say assuming that this device is powered by an external wall wart at 5 volts. So for today's design, we'll be using a Texas Instrument LDO that can support up to 3 amperes of continuous current. Operates from 2.7 to 5.5, which is well within our range. It's adjustable, so you can fine tune the output to give you enough headroom, and also save on the power dissipation. Next up is the 3.3 volt power regulator. This is going to power your peripherals and also the main MCU. The main MCU in the B series is the Nordic NRF52840 SoC that has Bluetooth and an ARM Cortex M4, which are all 3.3 volt compatible. So all the peripherals, our main MCU would be powered by this 3.3 regulator. We need to make sure that this particular regulator is able to supply at least 150 milliamperes. This is to operate the MCU and a few peripherals on the board. For today, we'll be using again a Texas Instrument switching regulator, just make things more interesting here. And the reason why we chose this particular regulator is because it's already in our supply chain. You may have a bigger design that uses a 3.3 volt rail. You can just derive power from it. And so, it's up to you. These days, regulators are getting fancier with, built-in power inductors and whatnot. Torex makes these tiny one package with built-in capacitors and inductors. You may want to try that, but we'll keep using what we have just because, supply chain would be happy with this. Next step is, how are we going to talk to the legacy device? RS-232 is a old reliable protocol. I even remember using my computer mice that had a DB9 connector. That does make me feel old. Anywho, if, say, for example, if you had a different interface, it could be, it could be CAN, it could be I2C, it could be GPIO, SPI, or any differential peripheral. You could, swap out that particular block with, whatever you want to talk with. And so today we'll be using an RS-232. It's a very well-defined protocol with plenty of parts available that do the translation for you. We are using a MAX 3232 chip, particularly because It's compatible with 3.3 volt logic. Older RS-232 converters are TTL 5 volts. That won't work in our case. So we are using that. It has built-in ESD protection, and it has 4 channels, which means I can do full hardware flow control, RX, TX, CTS, RTS. One tip here, as we go through these part selections, I don't know if anybody of you goes online and, maybe you go online and go on to digikey.com or Arrow or others, and try to see what the inventory is. But it's also helpful to do risk assessment, like what's the long-term availability of this part, what's the stock around this world, how long has this part been in the circulation. So you can go on to like Find Chips or Octopart, which are free services that give you a risk rank. So you can go into production knowing that this part would be available, or you can go to a more paid service like a Silicon Expert that will give you a long-term, more reliable, accurate analysis of that part. Next up, we're going to talk about the user interface. This device is going to be plugged into a legacy device, but does it need anything else? When building around the B series, we highly recommend that you at least expose the RGB system LED, expose the reset and mode buttons and USB and the SWB port. It's a 10-pin port that allows you to do step debugging. And so these things, you can remove them during production, but they're extremely helpful and critical during development. As your firmware engineer goes through the cycle of testing and evaluating, these would be extremely critical. So now that we have seen, to keep it simple, we'll be using LEDs, but if your project was more involved, it needed a touch screen or other bells and whistles, then you may also add that. Now that we know the basic components, what are we going to package this in? Like, is it going to be in a metal box, a plastic box, a custom 3D printed enclosure, or something else? In order to keep this webinar moving fast, we'll be using an off-the-shelf Takachi enclosure. This particular enclosure is it's a long part name. It's basically an ABS enclosure that has flanges, so you can easily mount them on a wall or keep them on a desktop. The backstory here is I was at a Embedded World Conference a few years ago in Germany, and they had this huge booth of Takachi enclosures. And the salesperson said, if you want to take all of these back home, that would relieve me of having to carry back these to Japan. So I ended up packing in a whole suitcase of Takachi enclosures. I would say that was my best conference trip ever. So I had one of these lying around, and I think I thought maybe creating this particular product with one of those enclosures would make the most sense. So that's why we chose this. But this also determines what antenna you'll be using. When it comes to antenna selection, if you have this project, say, for example, if we're inside a metal enclosure, you can't use a PCB antenna or a flex antenna. You'll have to mount it externally through an SMA or some other interface. But since it's a plastic enclosure, it's big enough to accommodate our off-the-shelf particle antenna. This antenna will also allow you to ride on the certifications that particle module already has, PTCRB, FCC. But also remember, just because the antenna has met all these requirements, that does not mean that it's going to perform just as well, because most of these certifications and datasheet parameters are done in free space. As soon as you put this antenna inside an enclosure, it's going to be a very, very different world. But that's a bigger conversation, and I think we'll talk about it in the future webinar. All right, but now that you have narrowed down on the parts, you know what that architecture looks like. Are you then going to directly jump onto designing a PCB, or are you going to prototype these parts? So an easy and quick way to prototype is using our evaluation board. You can just swap out this particular BSOM with a B402. Either way, it should work. It exposes all the GPIOs, also allows you to inject 3.3 or VCC power if you want to skip the built-in PMIC. It also allows you to try external SIM cards, memory storage. But say if you are too good to be using an evaluation board, and if you said like, no, I want to make my own design from scratch, you can do that too. I think the easiest way to do that is with the boron, because boron already has all the power management on it. And since it comes in a feather form factor, you can create or buy a feather wing. These feather form factors were introduced by Adafruit. They're all open source. So what I like to do on the Studios team is quickly, evaluate a particular part number. For example, on the left, you see the RS-232 level converter. Was able to quickly evaluate that if it works, that my footprints are right. So even without making the whole board, I can quickly evaluate these parts individually. I could also, make a BSOM to a feather adapter. I'll be open sourcing these designs later, so you can actually, maybe fast forward to this process. But there's a lot of value in creating these feather wings, and I like to call them as hardware design blocks or hardware building blocks, like Lego pieces that you're, able to use and test. So throughout the last few months, we have, explored what does it take to make a CAN bus transceiver. So make a feather wing that with a CAN bus transceiver, RS-232, RS-485, RS-422, or even more complicated things like a GNSS. You wanted to evaluate a GNSS. And so all these things help you evaluate the parts before you start jumping onto the final actual design. This also allows your firmware engineer to be unblocked in their firmware development, so they don't have to wait for you to debug your hardware and get them the board that is close to being final. Which brings us to the next question, and the next question is, what ECAD software do you use to design your PCBs? I'm gonna launch that polling right now. So looks like we have a clear winner, Eagle, but KiCad wasn't far behind. KiCad has grown into popularity recently. They have been doing amazing work. And Ultium, is the industry standard. I came from my previous career using Ultium, but at Particle we use Eagle just because back at the time when we started, all of our hardware was open source, and that was the most widely available software tool uh, for folks to try out. So that's awesome. Um, so the next thing we're going to do is we're going to jump into Eagle. So this is what we have been waiting for. So instead of just looking at and staring at slides, I'll share my screen and quickly go through the schematic, the PCB layout, and the mechanical integration that we do. We'll be using Eagle, but all of our libraries are available from GitHub. I will be sharing that link soon. So you can download or import those into other formats like KiCad, Allegro, or Altium. All right, let's do this. So here's the just one sheet schematic. It's an extremely simple, straightforward schematic. The first thing we're going to look at is the BSOM. The BSOM is an M.2 form factor. Along with the actual M.2 form factor, we also have pads available to connect your SWD port to. The SWD pins, the JTAG pins, are not exposed to the M.2. They're exposed separately. So if you are including this in an Eagle, you'll need to invoke this particular, where are you, invoke? There you go. And so you'll need to invoke the SWD port because it won't show on its own. Since it's an optional design, it doesn't show up by default. So you'll need to make sure you invoke that. We have a USB USB interface for the main MCU. So say if you wanted to debug over a USB over a serial, or if you wanted to load a new firmware, all of those fancy things can be done over USB. Every time you're exposing a connector to the external world, it helps to have a ESD protection of some sort. In my career at Particle, we have never had a case where a USB blew out the hardware, but you never know. You never know what circumstances you're working at. We have been using these things within lab, so we don't have to worry, but always helps to add. Remember, adding these parts like footprints are free, but board wristbands are not. So add them. We have an RGB LED that shows you the system status. People who have used Particle are aware that the system LED tells you what state the Particle product is in. Is it connecting? Is it connected? Is it getting an OTA update? All of those things. We also have an USB LED. It could be your first, sorry, not USB LED, one user-defined LED. That could be, your heartbeat or some status that you want to convey through just one LED. We have a couple of reset and mode buttons. I have also included an RC network for the reset line, just in case. And then a mode button. Both of these are active low. A couple of bypass capacitors. You won't be needing that because the BSOM already has them included inside. The next big block is the power supply. We are using like a barrel jack connector that you can plug your 5-volt wall wart in. We are separating these out into two particular power rails. One is the 4-volt DC that is going to power your modem, and then the second one is the 3.3 switcher. This particular LDO is adjustable. So right now, this particular combination of resistor gives you 4 volts or close to 4 volts. It also has an enable line. You can tie this back to your BSOM. That way you can completely disable the modem. But remember, the modems don't like their power to be taken away erratically. They have a specific power down sequence that you need to follow and then take away the power. For this example, we'll just keep the power on at all times. We are also including LEDs on every power net. Again, you can choose not to populate them, but it definitely helps as you're debugging. And then the last part is the actual level converter. We are using a max 3232, but you can use some a different one with higher or lower ESD protection. They have built-in charge pump circuitry that allows you to do the positive and negative voltages that are required for RS-232 physical interface. And we have a really old DB9. I think this is probably the first time I'm using this DB9 connector in my design, but it's a legacy, or I would, as I like to call it, retro. And the last but not least are test points. Sprinkle as many test points as you can all throughout the board. The future you will be very thankful to you. This will also help us during manufacturing. If you wanted to do a automated test fixture, these test points can be used to make sure that your device passes assembly, or if you wanted to load up a new firmware post-assembly. So there you have it. If you have any questions, please drop them in the Q&A. We'll get to them at the end. Then the next part is actual PCB layout. This is where the actual fun begins. It's like playing Tetris all day. You're routing and rerouting boards. And so right now over here we have an LDO, which is a low dropout linear regulator, and we have given it ample of copper to dissipate any additional heat. Using power planes to bring power in and out of the regulator. We have a switcher. Always follow the manufacturer guidelines when it comes to how to lay out a switching power supply. Texas has great online simulators and application notes that will help you guide through all of these. Most of this board was laid out on the top layer just because it's very straightforward and we have ample of real estate. But in your case, that might not be true. Then we have mode and reset buttons and the RGB LED. These are the pads that are underneath the M.2 form factor. So you'll have to populate pogo pins so that you can actually interface an SWD port to it. We have also exposed the USB interface of the modem itself. So this is separate from our MCU interface. This directly connects to the modem. And so if you wanted to update the firmware on the modem, the cocktail modem or the U-blocks, sometimes these vendors will give out updated binaries that need to be loaded. And the best and secure way to do that is through a physical interface. We recommend these test points, but I don't think you would end up using them. Again, footprints are free, board wristbands are not, and so it will save you a headache. We have a USB connector with a ESD protection, couple of status LEDs, a DB9 connector with the voltage translator. Um, but the whole board, as you can see, is it's a very unique shape, and this shape is dependent on what enclosure you use. I often find myself toggling back in between imperial and metric systems. When it comes to dimensions, like mechanical dimensions, I stick to metric, and when it comes to the physical board layout, I go on to imperial, because it's much easier to say that the trace is 20 mil than it is to say some decimal number of a millimeter. So stick to mils for layout, and dimensioning would be millimeters. Eagle also allows you to quickly verify your design. What would it look like in its physical manifestation by clicking on to the manufacturing. And over here, you can see if you have done any mistakes of putting the silk screen over something, or uh, missing out a particular via, just like gives you a good glimpse into what the physical board will look like before you press generate Gerbers and whatnot. You can see top and bottom, they look clean, so that's good. We'll also do a quick DRC run on it, and to see if anything comes up, do a check. Hopefully, let's keep our fingers crossed. Boom, nothing. So no errors is always a good thing, but you might have errors like overlapping solder mask, or the text is too big or too small, the traces are too close or not. And so that gives you a good idea that everything hopefully should work. And the fact that we have already tested this particular part with a feather form factor gives you more confidence that this design will work. Um, there's one other tip that I wanted to talk about in Eagle is variants. I don't know if you guys are aware. Variants allow you to use the same schematic, but decide which particular subsections will be populated or not. For example, these test points will show up as parts on your bill of material, and you don't want that. So maybe I can create a variant, or a variant called prototype, where these will be marked out. So when I generate a bill of material, these won't show up. Similarly, since it's a prototype, I'm installing all the LEDs and buttons and connectors. But if I want to go into production, I can go into production. These blocks would automatically be eliminated from your BOM, and give you a visual marker as to see that, for production, these parts are not going to be used. You may wonder what happens on the PCB side. Well, on the PCB side, the footprints still remain there. And that would be a horrific morning to wake up to, where the footprints are missing. All it does, it disables the paste layer from the PCB. So when you go into manufacturing, no paste would be applied to the parts that are not going to be populated. This visually will look good, and also give you a confirmation that those parts were intentionally not populated. So there we have it. We have a quick PCB. Now let's see how can we use this PCB into embed this inside an enclosure. The quickest way is to use, if you're using Altium, then it renders a 3D in which you can export. If you're using Eagle, you'll need to export that to the Fusion 360 environment. If you're using KiCad, again, you have native 3D support. So let's push this to the cloud. This is out of sync because we made a few changes this morning. But if you open up Fusion 360, the board will appear in its 3D manifestation. This will only happen if each component has a 3D model attached to it. If not, they will just appear as square blocks. But since we have done the job of applying 3D models, this particular design shows up in 3D. So this is extremely valuable when looking at any mechanical interferences that would happen on the board. The particle library for the BSOM comes with a 3D model. You can either get that as a Eagle library, or you can download it as a separate step file. So if you wanted to include this to any other footprint or library, you can do so. We have an SWD port here, a DB9 connector. So all looks good. Now we can bring this particular board into an assembly. And we were talking about using a Takachi enclosure. Takachi gives you 3D struct files if you ask nicely. All you have to do is email their FAE or salesperson, and they will ask you to sign an NDA. And after you sign an NDA, they give you this amazing step file. Using the step file, I can then, you know, decide what cutouts and where the cutouts would appear. So for example, this DB9 connector will need a cutout on its panel. The barrel jack connector will need a cutout on its side. So even before you put this thing together in, you know, the real world, you can assemble a physical assembly and simulate where all the parts will go. You can put the cover on it, and, you know, you will know that this is how my design will uh, work in the real world. You may want to, you know, design your own enclosure, but that's a rabbit hole that we do not want to chase in today's webinar. But there are plenty of resources out there. So there you have it. We have a complete product designed and ready to be assembled and deployed out in the field. So let's see what this product in its physical, real environment looks like. So we'll go back to the slides. And let me present again. And voila, you have a finished product that almost looks like its virtual counterpart. A confession here, I was pretty late on getting these PCBs made and delivered. So this was literally hand assembled and photographed last night. I went on to a local fast and PCB called Bay Area Circuits. So thanks to them, I was able to get these PCB spun up in 2 days, and, you know, assembled and tested. And since we already had tested these components individually, our confidence in the design is higher. And so the design works, all the files are available online. The one thing that I did not do is create the milled template for the faceplate. You can 3D print it or mill it. Takachi also gives you the option to get them pre-milled when you buy them. The antenna, as you can see on the left here, is mounted on the top of the enclosure. While it may seem that, oh, you know, you put an antenna and it should work, you may run into the issues of antenna performance based on the fact that there is so much metal around the antenna. The radiation pattern and its resonant frequencies might change. So you will need to pay attention to that and work with your antenna vendor or your RF lab to help you tune those parameters. But again, we'll talk about those things in a future webinar. And so there you have it. If you, before we jump on to, yes, I wanted to recap the key takeaways. For schematic, we talked about, you know, doing a risk assessment for the components before clicking the buy button, exposing the SWD, reset mode, and USB. Even if you are not planning on using it, remember to have them routed out to at least test points. Include LEDs to your power nets, add ESD protection where necessary. For PCB, we said, you know, adding test points are extremely valuable. They don't take up too much space, and, you know, they're free. Because when you design with a automated test fixture in mind, and, you know, these will come in handy. Create board variants so that you know the difference between prototyping to production. You can eliminate certain parts that are not required. And as I keep saying, footprints are free and board replacements are not. Remember to put in as much as you can and then take away the things that you don't need later. For mechanical, we zoomed through the whole idea of enclosure selection and antenna. But remember, just because you put an antenna somewhere inside an enclosure doesn't mean that's the best way to do it. So do an antenna study with your vendor earlier in the design, simulate your mechanical design, so you know that, you know, there won't be any mechanical interferences. This is all learned through the hard way, and I'm sure you'll make mistakes, but we are here to support you. Just give us a call, reach out to us on our community forums, or even if you are from the Twitterverse, come hang out on our Twitterverse and engage with us there. I will hand the next portion to Ethan to talk about what our future webinars will look like. By the way, the resources are all available on GitHub. Cal will share the link on our chats. And there you have it.
And time. Thanks, Mohit. Wow, that was incredible that we whizzed through that, through the schematic design, the board layout, the mechanical integration. And I hope this has been really valuable to everybody. And on that note, really is we've gone through kind kind of the really fun part of doing your IoT design and actually building the product. But we wanted to kind of address to say, hey, are there other topics in the product development cycle on the path from concept to mass production where it would be valuable for those of you that are building IoT products? Things like understanding, well, what antennas can I use? How can I certify it? In terms of manufacturing, how do I build my product on Particle and scale it to 1,000 devices with high quality and repeatability at my contract manufacturer? And also, how can I validate my product and actually say it does what it does? So what we'd love to ask everybody is which topics would be most interesting to you in a future webinar? It's really interesting to see as we have the answers coming in from all of you. Thank you for submitting. This is a judgment-free zone because the old adage goes, hardware is hard, and we want to be able to help guide those through it. All right. Wow. What oh, only by 2. Wow. Okay. So some of you are really seeing product design being really valuable and cloud connectivity being really valuable. And we appreciate you sharing that feedback, and we will go ahead and start getting hard at work on those webinars. Now, the next part, we wanted to give some time for everybody to be able to ask questions. I know you've been asking questions throughout the webinar. We appreciate that. But Mohit and I, and also our colleague Calvin Jepson is joining us, who's been answering your questions live in the background.
Awesome. Thanks, Ethan. And Mohit, come on back. I think if my watch was correct, you did it in about 33 minutes. So Woo! you under promised and over delivered on the building a product in 45 minutes. I just sent out a link to the resources, but I think the link I sent, Mohit, was broken. So, after this webinar, all of you attendees will get a thank you email, and we'll make sure to include the link to the resources in that email. So sorry about that, but we'll make sure we get you the information you need.
I believe that GitHub repository is currently private. I will open it up right after this webinar so you can access those files.
Great, perfect. But yeah, I think everyone's super excited to get their hands on what you built. And one of the great things about Particle is a good chunk of our hardware and IP is open source just for this reason. We want to foster innovation in our community, and we really value our community members. So thank you who joined. Looking through some of the questions, there are a couple that I wanted to address live. The first one, let's see if I can find it here. I want to make sure I give credit to the person who asked the question. I can't find the question, but it basically was, a question was, if we develop a prototype on the Boron and we want to scale on the B series, what aspects of the firmware need to be refactored? Either one of you, who wants to take that question?
I can take that one, and we'll give that shout out back to Bob Glicksman. When you're doing your conversion from Boron to B series, really the only thing that you can take into account is depending on your power management IC. So with the Boron, we've included a TI PMIC that has the libraries built into the device OS. So if you do take advantage of the PMIC features on the Particle Boron, when you move to the B series, you'll want to either include that same TI PMIC, which is available through our schematics, or if you haven't included it, there's not really much to do besides in Particle Workbench, which is the application development platform built on top of Microsoft VS Code. That IDE, you essentially pick, instead of Boron, you pick B series and you hit compile, and your firmware will compile.
So just to be clear, Ethan, other than, changing your logic around power management, everything else should be exactly the same, assuming you compile it for the right platform.
Yeah,
Yeah.
absolutely. Everything is exactly the same.
Yeah, one of the huge benefits of Particle is the abstraction of the underlying hardware and processor, such that you can migrate your code from platform to platform across different cellular SKUs or even across connectivity. Wi-Fi is another connectivity mode that we offer. Here's a tough one, and I have some thoughts on this, but from Trung Nguyen, if I need a product globally, which module is the best option? And let me try taking a stab at the start of this question.
Please.
This is a really, really good question. And it depends a lot on what sort of connectivity you require. As you should be aware, a lot of the 2G, 3G networks around the world are starting to be phased out, sunset, especially in North America and in Europe, where there are pretty good LTE coverage everywhere. One thing that's really tough about having a globally connectable SKU for IoT is a lot of the networks like Cat-M1 and Cat1, NB-IoT, there's no global standard. So certain countries will have one, maybe Cat-M1 like the US, but other countries will be standardizing on NB-IoT. So a global SKU would require really one to be able to connect to both of those. The other issue is that countries have different, and carriers have different roaming agreements. For example, Brazil does not allow you to have a SIM connect to roam inside Brazil for beyond, I think it's 60 days or some amount of time. And so globally connected SKUs, if you're talking about a single SKU that can connect anywhere for an indefinite amount of time, I'm going to go out on a limb and say that doesn't exist for IoT. It's not a particle specific issue. It's really just an issue with cellular networks globally. And so to answer your question specifically, Particle, the B523 would probably give you the best coverage across the most countries. We are working on a couple different new platforms and new modems that will give you even better coverage in the future. But for now, I would say the B523.
And that kind of dovetails into Gerald's question, where they had asked, you're offering a cellular module with Cat1 and LTE Cat-M1. What about NB-IoT, which offers better coverage and higher distances is the question. From what we found in our testing, the biggest challenge is actually the partnerships across countries, and different telcos actually implement NB-IoT differently. So whereas some, where you're familiar with LTE, 2G, 3G, they typically have connections that end up exchanging TCP/IP packets, even through a PPP connection. But what happens on NB-IoT is that the carrier will become the broker, and you don't actually, that doesn't allow you to move countries because only one carrier will allow you to send certain messages to them. The other thing is the throughput on NB-IoT is obscenely low. It's obscenely low, and the expectation is that you send only a few bytes every few hours, whereas many of our customers collect and shove data into the cloud as fast as possible. So we still keep an eye on it. And we've done early proof of concepts on NB-IoT, but not something that we've seen customers successfully deploying on just yet.
Here's a question from Scott Lemon. Scott, good to see you. Hope you're well. Question about the SOM to triple feather PCB that you showed, Mohit. Is that something that will be in the open source schematics? Do you know if it's something that we plan to sell on our retail store? Because I know it's not there right now.
Yeah, that's a good question. We do not manufacture those to be sold on the website. This is an internal prototyping tool that I developed on the Studios team to quickly evaluate new parts. But if you are interested in the design, there's nothing stopping me from sharing those files with you. So if you want to build your own or modify it, I'll be more than willing to share those files in the same GitHub repository that we linked earlier. We'll make that repository public as soon as we're done with the webinar.
Awesome. Question from Yangjoy Lee, asking about mesh and really local wireless communications. astutely pointed out that Particle used to have a mesh product, and Xenon was a part of that. And the question here is, how do you support this kind of application in the future? And I'll seed the question with Bluetooth, and ask Ethan for you to kind of address this question and what you think about it.
Yeah, absolutely. It was frustrating for us to have to pivot away from building out the mesh connectivity, but we've released what's called the BLE group, and we've invested more into the Bluetooth connectivity that the Particle devices can do. And majority of our customers were doing some kind of small star topology, where a boron was acting as a gateway, talking to some existing Bluetooth devices or another custom Bluetooth device. So through the BLE group, which you can find on the Particle IoT GitHub, you're able to actually take a boron and an argon and exchange messages over Bluetooth locally. Yeah.
Yeah, and I'll just add a big reason that we moved away from mesh and really thread was because we found that mesh means a lot of different things to a lot of different people. Sometimes people want to use mesh to extend connectivity into a mine, for example, or an area where there's not great connectivity in the basement of a building, in a parking garage. Sometimes what mesh means is you want multiple redundant cellular gateways and data routed dynamically to one or the other, depending on which one has better cellular characteristics. Sometimes mesh is just meant to be extremely, extremely low power, and you want to use it for devices that can last multiple years and only wake up on specific times. And we found that there was such a diverse set of different use cases across this, and the spec that we were using was still in development and wasn't as mature, I think, as we had originally thought. And so we decided to kind of turn our efforts towards cellular, which is really the bread and butter of Particle. And asset tracking, as you guys probably are aware, a new product that we sell. Question here from WeTech. Will the Boron 3G be supported in long-term future as a prototyping platform? What will be the M.2 product for the Boron 3G replacement? This is kind of a short answer. The B523 is the only Boron family product that supports 3G in an M.2 form factor at the moment. And I think that's your best bet going forward, to use that one if you're looking for M.2. Mohit and Ethan, if you guys see questions in here that you'd like to answer, go ahead.
I do see a couple of questions with a similar theme from John Brown as well as Chip. I think the idea is, how do we clearly distinguish between a boron and a B series? There are a few things that we need to take into mind. For example, boron is only available in the LTE Cat M1 SKU. If you wanted to use a LTE Cat 1 along with 2G and 3G fallback, you have to use a Quacktail module, which is much bigger. And so there is no boron equivalent for that particular module, because just the module is just physically so big. The second thing, nothing is stopping you from using a boron in your final products. You may as well, if the price is right, if the volume is right, you should definitely use that. But for example, if you wanted to include a particle module, which is a part of a much bigger design that already has power management, already has other MCUs, then it would make more sense to go the B series route, because it's a condensed down version. Or if you had a particular power requirement, say if you wanted a trickle charger from a solar cell, if you wanted to use exotic battery chemistries to power your B series, a boron, that could be more accomplished more easily through your own power management circuitry than relying on the borons. But there's no clear distinction. One is for prototyping versus production. You choose what best suits your needs.
And Mohit, to substantiate that statement, is it true that some of the projects that you build on the studios team are built around the boron and not the B series?
Yeah, we almost see a 50-50, depending on the volume and what the customer wants. We have deployed borons in actual micromobility products where you have electric scooters, sharing rides. We have used B series in utility equipment where they had their own power architecture already designed. And so it made more sense to include B series.
Great. We got a question about LoRa. Of course, LoRa always
Yeah.
comes up here. You know, it's something that we have, I think, thought about, you know, even before I joined 2 years ago, Particle. I came in thinking, hey, is LoRa a thing that we're going to support? Ultimately, what it comes down to is there, unlike, you know, LTE and 2G, 3G, if you're using LoRa, you have to manage the network yourself. And that's part of that adds to the complexity. You know, if you have a really big deployment, you probably should have a network administrator, someone who manages that network as their full-time job. And that's just not something that Particle has decided to invest in yet. There are definitely some great use cases of LoRa. I've heard of some really interesting cattle tracking use cases and other agricultural tracking use cases that require that sort of broadcast and low power functionality. Just not something that Particle is endeavored into, because we really want to rely on really ease of connection, and the people who are great at managing networks, AT&T, Verizon, and the others around the world, letting them do that rather than having our customers do it.
I wanted to add some clarity onto that as well. Is with LoRa and LoRaWAN, the bandwidth throughput is very very low, and there's different classes of LoRa technology. So typically, you know, LoRa is this high range, incredible battery life, sounds like the silver bullet for all connectivity solutions. The challenge that we've really run into is the throughput down to the devices and back from the devices. So with the Particle ecosystem, you're able to take advantage of our world-class world-class OTA, which really isn't something that's possible right now on LoRa or LoRaWAN, just because of the size of the communication. And secondly, right now there's not very many carriers that really have LoRaWAN. There's a Comcast network that we know is available, and there's the Helium network, but we really haven't seen real industrial applications deployed at scale with LoRaWAN globally yet. That's why we rely on LTE.
I see a fun question that could be elaborated in the future. Adam asks, what's the recommended hardware interface to program a B series at scale? Our recommended way to do it fastest is SWD or JTAG, because you can burn a complete binary in one go rather than having to upload application file, device OS separately. You can do either way. You can do it over USB or SWD, but our preferred way is that you do it over SWD, because it's more reliable and a faster way to do it. But having said that, there are more caveats when it comes to manufacturing. And I think we are working on a webinar in the future that will walk a user through the whole manufacturing process, both hardware, software, and cloud.
Awesome. We're at the top of the hour, so let's go for one more question. I have one in mind, unless Ethan or Mohit, you've picked one out of the crowd.
Go for it.
Okay, this is for you, Mohit. Could you quickly address the challenges of power supply design to handle 2G 2 amp transient spikes?
Oh man, I only have 1 minute to answer this. Long story short, it was a challenge. Back in the day when we designed it for the Electron, the recommended way, or the only way, was using a lithium polymer battery as a backup. So, as a almost like a bulk capacitance that will meet the 2 ampere surge requirements, because we were only using a USB, and USB cannot guarantee that it can support 2 amps of surge current. But modern USB laptops can do that, but you never know. So if you have a dedicated power supply, just make sure that you have enough headroom when you are calculating the power budget. If you don't, then think about using a bulk capacitance or a secondary battery to do the heavy lifting.
Awesome.
That's the long story short, but yeah, good question.
Nice 1 minute answer. Okay, the call to action here, Mohit or Ethan, you want to share your screen one more time on the slides? Well, I could just say it. If you guys have inquiries and want to know more about Particle, please visit our website, particle.io. We have tons of documentations. We have a community, but you can also email sales@particle.io to talk to one of our experts and get in touch with Ethan or myself. There you go. There you have it. Thanks, everyone. And we'll be
Yeah.
sending out an email. Ethan, go ahead. Mohit.
Oh, yeah. I was just going to say, for anybody whose questions we didn't get a chance to answer, we have the community and our Discord. The community is community.particle.io, and that information will be in the email that we send out. We'd love to continue the conversation with all of you.
Same here. Thank you so much for your time. Hardware is exciting. Please find us on support or Twitter or community to talk more about hardware and how one can design, or how we can help you design a product with Particle. Thank you so much.